Welcome to Network Security. Today, we are analyzing the architecture of one of the most critical components in network engineering, the firewall. Network engineering is defined by a constant structural tension. We require highly ordered private local networks to process sensitive information, yet those private networks must connect directly to the chaotic, entirely untrusted environment of the global internet. To resolve this tension, we deploy a firewall. This is the strict demarcation line between trusted and untrusted environments. Its entire function is to monitor and control the traffic attempting to cross that boundary. A firewall executes this control by evaluating incoming and outgoing data packets against a set of strictly predefined, deterministic security rules. If a packet meets the criteria, it passes. If it does not, it is dropped. Without this enforced perimeter, every host on an internal network is completely exposed. They are subjected to global scanning, unauthorized access attempts, and immediate exploitation by external threats. The most common mistake made by new network administrators is viewing a firewall as a single, static software tool. In reality, firewalls are tiered inspection engines. They operate on a sliding scale, forcing engineers to trade computational efficiency for depth of data analysis. We can map this trade-off directly to the OSI model. As we see in this vertical 7-layer stack, the firewall inspection zone spans from layer 3, the network layer, all the way up to layer 7, the application layer. To build a robust defense architecture, we have to construct it from the ground up. We will start by examining the fastest, most simplistic filters at the bottom of the stack, and gradually scale up to the highly intelligent, resource-intensive proxies at the top. Mastering perimeter defense requires precise calculations. You must understand the exact computational cost demanded at each step of this abstraction model. The foundational tier of perimeter defense is the packet filtering firewall, which operates strictly at layer 3 of the OSI model. This high-speed pipeline evaluates isolated packets against static access control lists. It makes drop decisions based solely on external headers, source IP, destination IP, port, and protocol. It never looks inside. This massive engineering advantage introduces zero latency, sustaining enormous data throughput. However, this speed comes with a severe architectural flaw. A standard packet filter is completely stateless. It retains zero memory of previous network events. This lack of memory means the firewall evaluates every returning packet in an absolute vacuum. If a packet arrives at the perimeter claiming to be a response to an internal query, the packet filter has no way to verify if an internal host actually initiated that request. External attackers routinely exploit this by spoofing trusted IP addresses or ports, crafting malicious packets that seamlessly match the static rules and bypass the filter. Layer 3 filtering effectively handles the initial calling of low-level network noise, but its blindness to broader context makes it structurally incapable of stopping targeted, intelligent intrusions. To solve the vulnerabilities of a stateless architecture, engineers developed the stateful inspection firewall. In this split-screen diagram, when an internal node connects, the firewall creates a dynamic state table to track that session ID. Monitoring the entire lifecycle, the logic gate actively checks returning external packets against this table, verifying an exact match before allowing traffic through. The logic shifts from filtering isolated data points to validating active two-way conversations. This context requires active processing. Continuously storing, updating, and querying thousands of entries in the state table consumes significant RAM and CPU cycles. Consequently, this memory requirement introduces a new attack vector. Adversaries can execute deliberate network floods, attempting to fill the state table with half-open connections until the firewall exhausts its memory resources and crashes. Despite the resource cost, stateful inspection elevates defense from evaluating random, isolated packets to tracking continuous conversations, neutralizing basic spoofing techniques in the process. This brings us to the next architectural problem. What happens if the connection is perfectly legitimate? The state table verifies the session, but the data payload itself contains a malicious script. To address this, we must shift our focus to layer 7 of the OSI stack, utilizing an application-level gateway, often referred to as a proxy firewall. Intercepting the session, the proxy firewall halts the packet and strips away headers to read the core payload. Operating at the application layer, it inspects raw content for malware signatures. If malicious code is identified, it executes a drop command and deletes the packet. Reconstructing, scanning, and repackaging application data in real time demands massive computational overhead. The trade-off is absolute. Layer 7 proxies deliver the highest possible level of security and network visibility, but they drastically reduce overall network throughput due to severe processing latency. Deep inspection guarantees payload integrity, but it forces network engineers to carefully calculate exactly how much speed they are willing to sacrifice for security. Modern enterprise networks require both high throughput and deep inspection. The engineering standard designed to resolve these competing needs is the Next Generation Firewall, or NGFW. NGFWs are highly consolidated architectures. They integrate standard stateful inspection, deep packet inspection, and intrusion prevention systems into a single cohesive hardware or software platform. This integration achieves true application awareness. Administrators can write granular security policies that analyze behavior, for instance, blocking all file uploads to a specific cloud storage service, while seamlessly permitting text chat on the exact same application. Running these heavy layers of concurrent inspection without crippling network speed requires intensely optimized algorithmic efficiency and dedicated processing hardware. By merging the high-speed routing of Layer 3 with the scrutiny of Layer 7, NGFWs provide a singular interface for enterprise-wide traffic control. Even the most advanced next-generation firewall operates within strict engineering constraints. Relying entirely on these devices leads to the perimeter fallacy, the assumption that a strong boundary guarantees internal safety. The first major blind spot of the perimeter is the massive proliferation of end-to-end encryption. As we see here, a data packet locked inside an encrypted HTTPS session slides straight through the NGFW inspection layers. Without heavily resource-intensive decryption modules, the firewall is entirely blind to the payload. If malware is encrypted, the firewall allows it through. The second structural blind spot is the human element, specifically social engineering. Consider a scenario where an internal user is tricked by a targeted phishing email. They click a malicious link, actively initiating an outbound connection to an external server controlled by an attacker. Because the internal user authorized the request, the firewall evaluates the session context, logs it as legitimate web traffic, and permits the connection. The third blind spot is the insider threat. A reinforced perimeter wall provides zero defense if the adversary is already sitting securely inside the trusted local area network. Firewalls are built to filter predictable threats attempting to cross a defined geographical boundary. They fail entirely when threats bypass the inspection engines or originate from behind the gate. Firewalls remain an undeniable requirement for network security. They enforce access policies, cull unauthorized traffic, and generate the critical audit logs required for anomaly detection. Yet their reliance on rigid logic makes them highly susceptible to configuration errors. A single inverted rule or overlapping access list can inadvertently expose the entire internal network to the public internet. Consequently, effective security relies on a strategy of layered resilience, known as defense in depth. This strategy demands a multi-layered approach. Perimeter firewalls must be paired with strict internal network segmentation, aggressive endpoint protection on individual devices, and continuous security training for users. Firewalls are the necessary foundation of network isolation, but deploying them as your sole security solution is a guaranteed architectural failure.